Welcome back, everyone. This is going to be a video about L'Hopital's rule. And lately we've been doing applications of the derivative. And this lesson is basically going to be our last application of the derivative. We've been learning about things that the derivative can do for us. And L'Hopital's rule is another one. So after this lesson, we'll be moving on to another portion of the course where we have another big topic to talk about. But let's go ahead and see what in the world is L'Hopital's rule. So let's go ahead and get started. Okay, so L'Hopital's rule, it is something that is going to help us with certain limit problems. So it's been a while since we've talked about limits, so I want to remind you a couple of things. So recall, we write the limit of f of x as x approaches a equals L if f of x approaches L as x approaches a. I mean, we know this, but I just want us to get into the right mindset. We had a full definition of the limit earlier in the semester, and this is just kind of the short version of that definition. Let's see, we could also remind ourselves that a limit can be defined even if f of a is not. And we saw that visually with some examples earlier in the semester where we would have a graph with a hole in it, and maybe the hole in it means that the function is not defined at that point, but the limit could still be defined. Or not, sometimes it is, sometimes it isn't. And informally, we can think of the limit as x approaches a, f of x, as the y value that the graph approaches. As x gets closer and closer to a. Now, that's kind of the informal version. Earlier in the semester, we had the official definition. We went into some more detail about what it means to get close to something and what does this word approaches mean. We said arbitrarily close, things like that. So we talked about limits really at the beginning of the semester, back before we even knew what the derivative was. And now we're going to see a technique involving derivatives that's going to help us solve some limits. So in a way, it's like we've come complete circle because we learned about limits to help us define the derivative, and now we're going to use the derivative to help us do some limit problems. All right, so let's go ahead and let's look at an example of a limit that we did a long time ago. I think this is exactly a problem that we've seen before. If not, it's definitely the same form as some problems we've seen. The limit as x goes to 1 of x squared minus 1 over x minus 1. And I'm not exactly showing you L'Hopital's rule yet. We'll get to that pretty soon. But how would we deal with this in the beginning of the semester when we first saw limits? I mean, you say, okay, x is approaching 1. You might think about what's happening to the numerator and what's happening to the denominator. Well, if x goes to 1 in the numerator, then the numerator looks like it's going to 1 minus 1, which is 0. And in the denominator, it also looks like it's going to 1 minus 1, which is 0. So I'm going to say that this looks like 0 over 0. Looks like is not a very formal mathematical term, but we've seen limits like this before, and we know that it might actually equal something if we factor and cancel. So that's how we dealt with this. We factored and canceled. We said, hey, that numerator factors into this. And then once you've factored it, it's okay to cancel those terms. Limit as x goes to 1 of x plus 1. It's a lot simpler now. And this thing right here is a polynomial. It's a simple polynomial. We had a theorem back then, or a rule back then, that said if you are left with just a polynomial, then at that point it is okay to just put in x equals 1. And that's because polynomials are continuous across all real numbers. So this does equal 1 plus 1, which is 2. So the thing that I wanted to draw to your attention is that at first glance, this problem kind of looked like 0 over 0. And it's tempting to just say, oh, well, that's undefined. You can't divide by 0. Look at the denominator. It looks like 0. However, remember, limits say that x approaches a. So x is approaching 1, but it's not actually equal to 1. There's a difference, right? It's getting closer and closer to 1, but it's not really 1. So the denominator is not really 0. And in fact, this whole thing evaluates to 2. I'll show you another one. Remember we had a lesson about limits involving infinity? How about one where x approaches infinity? We saw limits that looked something like this back in that lesson. Whoops, let me move the page up. Now, infinity is not a number. Infinity is sort of a concept that x can approach, but x will never actually equal infinity. Infinity's not a number that I want to see you just substituting in for x. Don't say infinity squared, right? But we can imagine that x is growing arbitrarily large. X is a million, a billion, a trillion. It keeps growing and growing. So what's happening to the numerator and what's happening to the denominator? I would say that this looks like infinity over infinity. Maybe I should put these in like quotation marks because these are sort of a... It's not really 0 over 0. It's not really infinity over infinity. But that's just what it looks like at first glance, because I'm imagining this numerator, x squared. If x gets incredibly large, then x squared gets incredibly large. The minus 1 is pretty insignificant. And then on the bottom, the x squared gets incredibly large. The little plus 1 is pretty insignificant. Yeah, it kind of looks like both the top and the bottom are approaching infinity. But we learned back then that there are rules for how to deal with this. We actually learned a shortcut based on the degree of the numerator and the degree of the denominator. Right? And you could just use that shortcut, and I think you know what the answer to this is. But I'll show you how you would do it with algebra without the shortcut. Just to remind us of why does that shortcut even work? Shortcut is you take the coefficient in front of x squared here, coefficient in front of x squared here. I think the answer is going to be 1 over 2. But why does that rule work? It's because you could use algebra, multiply by something over itself. If you multiply by 1 over x squared over 1 over x squared, you get this. I think we did something like this just for one example back in that lesson. I'm doing it again now. This kind of algebra. The point of this is that now x is approaching infinity, so 1 over x squared, that term is approaching 0, and this 1 over x squared is also approaching 0. So overall, I'm getting 1 minus 0 over 2 plus 0, and that's why the answer is 1/2. That's why that shortcut works, because of algebra steps like this. So what do these two examples tell us? Why am I revisiting old limit problems? I guess I wanted to say that even if at first glance a limit looks like 0 over 0 and you're tempted to say it's undefined, or it looks like infinity over infinity and you're tempted to say, well, I don't know, what would you say? Would you say that's undefined? Would you say that equals 1? Well, in fact, it equals 1/2, and this one equals 2. So the point is, you can't always tell what a limit is going to be based on, a quick glance like that. You can't just imagine substituting in 1, because that's not how limits work. All right, now these limits, these types of limits, have a name. These types of limits, which I'm going to say are of the form 0 over 0 and infinity over infinity. That's kind of the category. That's kind of the type of limit that we're talking about. These are called indeterminate forms. These are limits that are indeterminate forms. And this discussion we've had so far shows us that we already know how to deal with some limits that are indeterminate forms. We did it back in the beginning of the semester, either by factoring and canceling, or by using algebra or rules to help us deal with these situations. So we already know how to deal with some limits that are indeterminate forms. The point of this lesson is that as of right now, we don't know how to solve all indeterminate forms yet, and we need an extra tool to help us with some of them. I'll show you one. I'll show you one that we're actually not ready to solve yet, but we'll be able to solve very soon, in a few minutes. What if you had the limit as x approaches 1 of ln x over x minus 1? Okay, so we could think about the top and the bottom, like what's happening to the numerator and denominator. As x approaches 1, the denominator looks like it's approaching 0, 1 minus 1. The numerator looks like it's approaching ln 1. Well, ln 1 is 0, right? We know ln 1 is 0 because e to the 0 is 1. So I'm going to say that this is, instead of using the phrase looks like, I'm going to say this is an indeterminate form of the type 0 over 0. Okay, instead of saying looks like, we use the phrase indeterminate form. So up above, we solved some limits that were indeterminate forms. How are we going to do it for this one, though? We can't just put in x equals 1. We know that. We would get 0 over 0, and we know that that doesn't work for ones like this. We don't just put 1 into the expression. However, with this problem, the issue is that we can't really rearrange, factor, or simplify. I don't see any kind of factoring or simplifying or algebra trick that's going to help us this time. We need a new trick to help us with limits like this, when there's no factoring that can be done or anything like that. Oh, by the way, didn't we also deal with some limits back then by multiplying by a conjugate over a conjugate? I guess that was another algebra trick, but that's not going to help us here. There's no square roots. So the new trick that's going to help us with some indeterminate form limits, it's going to be called L'Hopital's rule. So this is a French name. It has an apostrophe after the L, and it has an accent over the O. L'Hopital's rule. And I've also seen it written as this. So, I mean, either one is fine. I'm just telling you in case you see it written in two different ways in a textbook or the internet or whatever. And it says, if a limit as x approaches a of f of x over g of x is an indeterminate form of the type 0 over 0, or I guess you could say above the two indeterminate forms that we talked about were 0 over 0 or infinity over infinity. It could actually be plus or minus infinity over infinity. I mean, if it was minus infinity over infinity, then we'd still have the same kind of issue. All right, then L'Hopital's rule is actually going to be just a really nice formula. And it's not something that's hard to memorize. It's actually just going to tell us what the limit is. You should be expecting that it's going to use the derivative at some point, because I said this was going to be an application of the derivative. The limit that we are trying to evaluate, the limit of something over something, so there's like a numerator and a denominator function. All right, ready for this formula? It equals the limit as x approaches a of f prime of x over g prime of x. Yeah, the derivative of the top and the derivative of the bottom. I do have to say, provided that this second limit exists or is infinity or negative infinity. That's just a little disclaimer. But yeah, this is L'Hopital's rule tells us that if you have one of these indeterminate forms, which they seem pretty common with limit problems, a lot of limit problems are in these kinds of forms, that one way that you can solve them is actually you still have a limit. All right, the limit of this equals the limit of that. So you still have limit as x goes to a, but you take the derivative of the top and derivative of the bottom. And that's not very hard to remember. I mean, derivative of the top, derivative of the bottom. It's not a complicated formula. So note, this rule also works for one-sided limits. And limits at infinity. So I wrote the formula above with x approaches a. And I guess what I'm saying now is it also works if x is approaching a with a little plus sign, if x is approaching a with a little minus sign, if x is approaching infinity, and if x is approaching negative infinity. The same formula, just change x approaches a. It also works. So now what I'd like to do is I'd like to answer that question from before. And we're going to apply L'Hopital's rule because I said it didn't look like there was any factoring or algebra. The whole point of this is we needed this new trick. So let's try it on this problem. This will be our first L'Hopital's rule problem. Okay, well, we already identified that this was an indeterminate form, but I'm going to write it again. I'm going to abbreviate it. Indeterminate form of the type 0 over 0, which means we can use L'Hopital's rule. I want to point out to you before I move this off of the screen, L'Hopital's rule is stated saying if the limit is an indeterminate form, then you can use this formula. So we don't use this formula necessarily for every limit in the world. We use it for these types of limits, which this is. So let's use it. It says that this equals the limit as x approaches 1 of the derivative of the top over the derivative of the bottom. Now, when you take derivative of the top, derivative of the bottom, that changes the function. Like ln x over x minus 1 is different from this function now, right? So as functions, they are not equal to each other. But as limits, they are. The limit of this equals the limit of this. So let's do this. We know these derivatives. Derivative of ln x is 1 over x. Derivative of x minus 1 is 1. So this whole thing simplifies to this. What happens to 1 over x as x approaches 1? It just becomes 1 over 1, which is 1. All right, so that was us applying L'Hopital's rule to solve this problem. This limit actually equals 1. Let's do another one. The limit as x goes to 0 of 3 to the x minus 2 to the x over x. First of all, is this an indeterminate form? Is there some other way we can do this? Well, let's see. Think about what happens to the top and bottom. The bottom definitely goes to 0. The top goes to 3 to the 0 minus 2 to the 0. Well, that would be 1 minus 1. So yes, this is an indeterminate form of the type 0 over 0. So L'Hopital's rule does apply, meaning this equals the limit of d dx of the top over d dx of the bottom. These two limit problems. These are ones that I couldn't really give you at the beginning of the semester because we didn't have this trick yet. And we couldn't really talk about L'Hopital's rule back then because we didn't know about derivatives yet. So that's why this fits in perfectly here. The derivative of the top is 3 to the x ln 3, and then minus 2 to the x ln 2, and the derivative of the bottom is just 1. Exponential functions are continuous, so it is okay to just plug in 3 to the 0 and 2 to the 0. So this is 3 to the 0 ln 3 minus 2 to the 0 ln 2. Notice that I didn't write limit in front of this step because we've already evaluated the limit. You should put equal signs between expressions and you should write limit in front of limits, but I'm not writing it here because we already dealt with it. This is ln 3 minus ln 2. Is that the answer? Yeah, I mean, that's basically it. I guess one thing we could do that might make it look a little simpler is, remember a little property of logarithms that says you can combine this? I like that for this answer. Logarithm minus a logarithm, you just combine it into that. That's the answer. And wow, looking at this problem, I think we really couldn't tell, like, at first glance, you might look at this and say, it looks like 0 over 0. I don't know what it's going to be. I would not have guessed that the answer would be this, ln of 3 halves. It's some kind of decimal. It's around 0.4. But yeah, it's a real number. Notice both of these problems we just did were indeterminate forms of the type 0 over 0, but we get different results. So just because it's in the same form doesn't mean you're always going to get 1, for example. The 0 over 0 form can lead to different results, different answers. We should look at some infinity over infinity examples. I want to show you an infinity over infinity example from earlier. Actually, we did this today, but I want to redo it using L'Hopital's rule to show you that this also works. So it was the limit as x goes to infinity of x squared minus 1 over 2x squared plus 1. Now, I can think of 3 ways to solve this. All right. Number one, we could use that shortcut. Coefficient in front of x squared, coefficient in front of x squared. The answer is 1 over 2. That's the first method. Method number two, do what we did earlier in this video and do some algebra. We multiplied by something over something, and yeah, we also got an answer of 1/2. Method number three is L'Hopital's rule, because this is, I'm just going to actually say it's an indeterminate form of the type infinity over infinity. Indeterminate form of the type infinity over infinity. So yeah, we could do this with L'Hopital's rule. Actually, you know what? I'd like you to try doing this with L'Hopital's rule. You could pause the video for a moment and give it a shot. All right, so we do limit of the top, derivative of the top, I should say. I mean, we know what the answer is going to be. We know it's going to be 1/2. But I wanted to show you that this is another way to deal with these kinds of problems. Derivative of the top is 2x. Derivative of the bottom is 4x. The x's cancel. We wind up with 2 over 4, and 2 over 4 simplifies to 1/2. So now this is a new way for us to solve these kinds of problems if we want to. Multiple ways to get to that answer. I'll show you a tougher one. Let's do it. Let's do a new one. I'll do this one for us. How about we want to evaluate x goes to infinity of e to the x over x squared. It's not really that tough, but I'm going to do this because something a little bit different is going to happen. So whether you call it the form or the type, you identify that this looks like an infinity over infinity case. So we want to use L'Hopital's rule. We're going to do the limit x goes to infinity, d dx of the top, d dx of the bottom. And what do we get? Well, these derivatives are not that hard. This is e to the x, and this is 2x. But what happens now? What happens now? What do we do? We did L'Hopital's rule. In the previous problems, when we did L'Hopital's rule, we got to the answer pretty quickly after that. This time we did L'Hopital's rule, and we still are wondering, like, well, what does this equal? Let's think about what happens to the top and bottom. The top is going off towards infinity. The bottom is also going off towards infinity. So what's happening here is we still have an indeterminate form. And how do we deal with indeterminate forms? We use L'Hopital's rule. So we're going to use L'Hopital's rule a second time. Derivative of the top, derivative of the bottom. Now, you might be worried, are we stuck in some kind of loop here? Are we going to be doing L'Hopital's rule over and over again? But actually, I think that this is going to work out because we started with a problem that had x squared on the bottom, and then we got to a problem that had 2x on the bottom. And now I think we're going to get to a problem that just has a 2. So it feels like the problem is getting simpler. It feels like it's headed in the right direction. Actually, look at this. This is not an indeterminate form anymore because the bottom is just 2. In fact, that 2 you could pull out front as like a 1/2. So 1/2 limit x goes to infinity, e to the x. Yeah, e to the x is approaching infinity. The multiplying by 1/2 or dividing by 2 is not really going to stop that. So the answer is infinity for this one. So there are two things that we can learn from this problem. First of all, we learn that sometimes you have to apply L'Hopital's rule more than once. We used it here, and we used it here. And the other thing to learn is that sometimes these answers could be infinity. You know, they could be infinity or negative infinity. Sometimes you could even have a problem where you might need to use L'Hopital's rule 3 times. Or four times. I don't know if we'll see any that need it 4 times. It's basically because of this x squared here. I guess if this problem had an x cubed, then we would probably need to use L'Hopital's rule a 3rd time. All right, let me give you one to try. I want you to try this. The limit as x goes to infinity of 3x squared plus e to the x over e to the x plus 1. So pause the video and give that a shot. Okay, so, yep, this is another infinity over infinity case. Indeterminate form. So we want to take derivative of the top, derivative of the bottom. I'll show you a little trick. Sometimes when we do L'Hopital's rule, this is up to you if you want to write it this way or not. But sometimes, instead of writing the ddx's, let's just do the limits. I mean, do the derivatives. Like 3x squared, I know that's going to get me 6x. E to the x is the derivative of itself. The bottom is e to the x. So I took the derivatives, and sometimes in order to indicate that we used L'Hopital's rule, sometimes people will write a little L apostrophe H over the equal sign to indicate that in this step I applied L'Hopital's rule instead of writing the ddx's. I like that. I do that sometimes. I think it's a pretty cool little notation. Oh, wait, what do we need to do now? So look at this. 6x plus e to the x over e to the x. You could say that this is still an indeterminate form, and you could use L'Hopital's rule again. I see 2 different ways that we could deal with this. All right, how about this? One way, and you might have done it this way, is apply L'Hopital's rule again. So what's the derivative of 6x? That's 6. We get this. Looks like the numerator is going to infinity and the denominator is going to infinity. We could apply L'Hopital's rule again. And we get e to the x over e to the x. Ah, well, this is also an indeterminate form, right? It's infinity over infinity case. And you might say, well, wait a second. If I apply L'Hopital's rule to this, like, it's just going to equal itself. We're just going to keep being in a loop, getting this like, over and over and over again. Well, here's the thing. E to the x over e to the x is 1. So don't apply L'Hopital's rule. Just say something divided by itself is 1. So the answer is 1. So that's one way to solve this. I saw another way to solve this that I think I'm going to show you. I did L'Hopital's rule at the beginning, and then from here I kind of branched off and did some other steps. And I want to show you that this also gets us 1. I saw this expression and I said, hey, you know what? There's an e to the x on the bottom. There's an e to the x up top. It might actually work out nicely if I split this up. So I split it up like this. The nice thing about doing that is you get this. You get kind of a 1, e to the x over e to the x. And then what did I do? I guess then I said, this is the limit of 6x over e to the x as x goes to infinity, plus the limit as x goes to infinity of 1. Like, you can split up limits, right? Limit of the first piece plus the limit of the second piece. Then I applied L'Hopital's rule to the first term. I don't know, should I put the apostrophe LH here? Yeah, I guess I should. We're applying L'Hopital's rule just to this first piece. So I got a 6 over e to the x. And that other limit is just 1. So let's just put 1 here. And then I said, okay, this piece, 6 up top, e to the x on the bottom. As x goes to infinity, the bottom is going to grow incredibly large, astronomically large, while the numerator is just a tiny little number 6. So that whole thing is going to approach 0. And then we still have the plus 1, and I got 1. So that's two different methods, I guess. The method up top, the method up top where we use L'Hopital's rule 3 times, that's pretty straightforward. There's nothing wrong with that. I just saw this as another way to do it. I guess I wound up using L'Hopital's rule twice with this method. So I think you're ready to do problems like this and problems like the 0 over 0 examples that we did. There's something else I want to talk about, though. There are also other indeterminate forms. Besides those two main ones that we talked about. And some of these forms are a 0 times infinity case. This is the limit as x goes to a of a function times a function where one of these functions approaches 0 and the other approaches infinity or approaches negative infinity. We'd have the same issue. So that's an indeterminate form because it could actually equal 0, or it could actually equal infinity, or it could actually equal some finite number. It could equal 1. It could equal ln of 3 halves. It could equal 1/2. We don't know. So we're going to have to talk about how to deal with limits that are like that. Another one is something of the form infinity minus infinity. Now, I'm putting quotation marks around this because remember, I said infinity is not a number that we just want to toss around like other numbers. Infinity is more of a concept. So this is kind of how we describe the form. You could say it's an indeterminate form of the type infinity minus infinity. And this would be the limit as x approaches something of a function minus a function where both have the same limit of infinity or negative infinity. So it could be infinity minus infinity, or it could be negative infinity minus negative infinity. It's also a problem, or it's also an indeterminate form. And what I mean by this is it's not one of each. It's not like one of them approaches infinity, one of them approaches negative infinity. They both have the same limit. The strategy for these two indeterminate forms. Now, L'Hopital's rule, as we stated it earlier, officially L'Hopital's rule only applies to the 0 over 0 or infinity over infinity case. It didn't say anything about these. So the strategy for these is we can rearrange into the 0 over 0 or the infinity over infinity form. And then use L'Hopital's rule. Then L'Hopital's rule. Okay, so I'll show you an example. Let's say I want to do the limit, and I'm going to make this one a one-sided limit. Earlier I said that this discussion also applies to one-sided limits. So let's have one that is a one-sided limit. and I'll talk us through this. So notice that x is approaching 0 and ln x is approaching. Let me ask you, what is ln x approaching here? Do you know what is ln x approaching as x approaches 0 with a little plus sign? Negative infinity. How do I know that? How do I know this is going to negative infinity? It's because I remember the graph of ln x looks like this with a vertical asymptote. All right, so in my head, I was thinking about this graph, this vertical asymptote on the y-axis, and I was saying, well, if x approaches 0 from the right, that's what the plus sign means, then y is getting lower and lower and lower. It's going to negative infinity. All right, so this is an indeterminate form of that type, 0 times infinity. The suggestion is we try to rearrange it into one of the more familiar forms. How do we do that? How do we rearrange this into one of those forms? Well, here's a cool little trick. Instead of writing it as a product, this is x times ln x, we want to get it into the form of something over something. We want it to look like a quotient. Right now, it doesn't look like something over something. It's a product. Well, one way to turn a product into a quotient is instead of multiplying by x, I'm going to divide by its reciprocal. Multiplying by x is the same as dividing by 1 over x because it's reciprocal. And now it's in infinity over infinity form. Just by doing that, just by rearranging it to be something over something. So the rest of this follows kind of like a normal L'Hopital's rule problem. You could say this is the limit of d dx of the top over d dx of the bottom. You know what? Instead of writing it as 1 over x, how about we make it x to the negative 1? It's easier to differentiate in that form, isn't it? All right, let's take those derivatives. And the top gets me 1 over x. And on the bottom, I get derivative of that is going to be negative 1 over x squared. And then we have to figure out, like, what's going on with this? Is this an indeterminate form? What's happening to this if x is approaching 0 from the right? Well, it's a fraction over a fraction, so we could probably find a better way to write this and see if any of those x's cancel out. How about we write it as 1 over x times negative x squared over 1. Yeah, I guess what I did was I took the bottom one and I said instead of dividing by that fraction, I'm going to multiply by its reciprocal. That helps me see that we have things that cancel out. We have a lot of things that cancel out, actually. The 1 over 1 is gone. The x squared over x is going to just leave me with x. And there's a minus in front of it. So I have this. And what happens to negative x as x approaches 0 from the right? It approaches 0. So that type of problem, it was mainly about rearranging it into one of those forms that we could apply L'Hopital's rule to. I have another one to show you. I think for the next one, I'll start it out and then I'll ask you to finish it. Suppose we want to do the limit as x approaches 1 from the right of, ooh, this is an interesting one, x over x minus 1 minus 1 over ln x. Let me start this one out for us. Let's talk about this. Like, what form is this? We should think about what's happening to each term, I guess. So what's happening to the first piece? As x approaches 1 from the right, the numerator is approaching 1, from the right. So imagine it being like a little bit bigger than 1. And then the denominator, well, it's approaching 0 from the right. So actually, the numerator being around 1 and the denominator getting closer and closer to 0 means that this piece is approaching infinity. The second piece is 1 over ln x, where x is approaching 1 from the right. We said earlier that ln of 1 is 0. This is approaching that from the right. So again, this is something that's 1 divided by something that's approaching 0 from the right. So this is also approaching infinity. So I want to say that this is of the form infinity minus infinity. Yeah, so the discussion above said that for this type of form, we want to try to rearrange it into one of the other two forms, right? So here's an idea. How about we try to make it one fraction? It's two fractions, and if we're going to try to rearrange it, look up here, we're going to try to rearrange it to one of these forms. These are just one fraction. So yeah, let's try to do a common denominator, and that would at least get it into one fraction, and then we could figure out what to do from there. So a common denominator would be found by just multiplying the denominators. What does that do to the numerators? Makes it x ln x minus x minus 1. All I did right here was algebra. I didn't do any derivatives. I didn't do any L'Hopital's rule. Just working with fractions. How do you combine two fractions? You combine them with a common denominator. You adjust the numerators appropriately. Okay, so let's evaluate. Let's figure out what's going on with this now. Think about as x approaches 1 from the right. Okay, so I have something approaching 1, something approaching 0. So that first little piece there approaches 0. Minus 1 minus 1 is 0. So the numerator is approaching 0. The denominator, because of this x minus 1, is also approaching 0. So this is of the form 0 over 0. Yeah, so just by combining it into one fraction, we actually got it into one of those more familiar forms. Now we can apply L'Hopital's rule to this. So I'd like you to try to finish it from here. I'm going to suggest that you pause the video and see if you can finish the problem. All right, so did you apply L'Hopital's rule? ddx of the top, ddx of the bottom? How about I just write it like this? Derivative of the first piece, derivative of this. All right, there's my ddx of the top, and then ddx of the bottom. Oh, wow, we have to use the product rule. I guess most of the derivatives that we've done today have been very straightforward. We haven't even really needed the chain rule or the product rule or the quotient rule, but we're using it now. So this is a little product rule problem. So x times 1 over x plus ln x is what I get from the product rule on that. And then minus 1 from that other piece. And then the denominator, I'm going to apply the product rule to that also. I get x minus 1 times 1 over x plus ln x. And we'll try to simplify this a little. I mean, check this out. Watch this. We have x times 1 over x minus 1. Those cancel because that's 1 minus 1. So yeah, we could write this as just ln x up top. And then what is it over? Let's just distribute these parentheses here. It's going to be 1 minus 1 over x plus ln x. Now, is that any better? Like, is that simpler? I would say yes. Compared to this, compare these two lines, I think the bottom one is simpler. So I think L'Hopital's rule has helped us to get the problem into a nicer form, but we're not finished yet. It turns out that this is also, if you look at it carefully, this is also in the form 0 over 0. So let's use L'Hopital's rule again. Derivative of the top, I know what that is. Derivative of the bottom, that's not too bad. So I guess we get, remember, I'm writing the limit as x goes to 1 with the plus sign in front of every one of these. Make your work make sense. Equal signs, limits. The numerator is 1 over x. The denominator is, we know the derivative of 1 is 0. The derivative of minus 1 over x is 1 over x squared. And then the derivative of ln x is 1 over x. Okay, is this an indeterminate form? Well, look at this. X is approaching 1. So if x is approaching 1, numerator approaches 1, denominator approaches 1 plus 1. Yeah, so now we can just say 1 over 1 plus 1. Answer is 1/2. That's the final answer. So here, we'll fit the whole problem on the screen. So that was a tough one. It was tough because first it was in that infinity minus infinity form, and we had to try to find a common denominator, combine it into one fraction, and that got it into this more familiar form. Then we started applying L'Hopital's rule, but it turned out that we needed to apply L'Hopital's rule twice. So this was probably the toughest one that we've done today. And it used the product rule also, so that was nice. It's always good to revisit some of those rules. So it turns out that there are also a couple of other indeterminate forms, and what I want to talk about next are indeterminate powers. We don't see these as often, but suppose we have a limit of a function raised to a function. I mean, we've seen functions raised to functions before, but maybe not a limit problem like this. Suppose we have this where the limits of f and g are I'm going to put a little star here. Could be 0 and 0. This would be an indeterminate form of the type 0 raised to the 0. Or suppose they are infinity and 0. Then we call it an indeterminate form of the type infinity to the 0. Or one more. Suppose that the limits of f and g are 1 and plus or minus infinity. We call this an indeterminate form of the type 1 to the infinity. And these could also turn out being infinity or 0, or they could also turn out to be something like 1/2. We don't really know. It depends on the problem. The strategy for these is we let y equal this f of x raised to the g of x, and then take ln of both sides. So you get ln of y equals ln of the right-hand side. We have a property of logarithms that says when you have a logarithm, which could be ln, of something raised to a power, that you can bring the power out front. Right? Like this. So I brought the g of x out front. And then we work with this. We work with it from here. And, you know, we can also get our answer back in terms of y. You know, this actually looks like we have ln of y equals this. And, like, I'm saying we're going to work with this, but this is not really y. This is ln of y. So, I guess I should say, and to get, we basically get an answer for ln y, and then to get our answer back in terms of y, we use the fact that y equals e to the ln y. So what I'm saying is you have a problem. It's y equals this function. It's a function raised to a function. You take ln of both sides, and then you work with this expression, g of x times ln of f of x, and you find the limit of that. That gets you an answer for ln y. To get an answer for y, you do e raised to what you found. So it's like basically you're changing the problem by doing ln, and then you need to change the answer back by doing e raised to that. Now, the setup here, it kind of feels reminiscent of something we talked about called logarithmic differentiation. But remember, what we're doing is not logarithmic differentiation here. Back when we were doing that, we weren't dealing with limits. These are limits. So the idea of taking ln of both sides is the part that's reminiscent of that, I guess. So I just spent half a page talking about indeterminate powers. And what I want to tell you is I'm actually not going to test you on this. This was something I just wanted to spend a few minutes talking about. But really, I wanted to address it so that you know that these types exist. But I'm really more interested in the previous indeterminate forms. So the ones that you need to know are the 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity. Okay? The ones that we did example problems of. Now you know that these also exist, and they show up kind of rarely. Maybe in Calculus 2 you might see one of these at some point, but it's not very common. Okay, so now you know the indeterminate forms that we're the most interested in, and let's do a couple more example problems before we finish today. So I was thinking about it, and I thought you could use a couple more examples. So I'm going to ask you to try these. I'm going to give you 2 of them. And, you know, I'm not going to tell you what form these are in or anything like that. You figure it out. There's going to be a part A, limit as x goes to 0 of ln 1 minus 3x over x. And part B, limit x goes to 0, e to the 3x minus 1. All of that is over ln 1 minus 4x. So I'd like you to pause and give these a try. All right, so we apply L'Hopital's rule to these. Let's work through these. Actually, these are both the same form, aren't they? The same indeterminate form. Actually, this is of the form 0 over 0, and this is of the form 0 over 0, using the fact that we know ln of 1 is 0, and e to the 0 is 1. So yeah, these actually do wind up being 0 over 0 type. So let's work out the solutions. For part A, I applied L'Hopital's rule. We still write the limit out front. And what's the derivative of ln of 1 minus 3x? I mean, you could do some scratch work off to the side if you want. It's a chain rule problem, right? ln of 1 minus 3x. By the chain rule, I know the derivative of ln x would be 1 over x. So I'm thinking it's like 1 over 1 minus 3x times the derivative of the inner function. So if you're able to do that chain rule in your head, that's okay. If you're not, then you can just write out the steps for it. And then the derivative of the bottom is 1. Let's see. This is over 1. I don't like the over 1, so let's just get rid of that. Dividing by 1 doesn't do anything. All right, as x goes to 0, is this an indeterminate form? No, the top is -3. The bottom is 1 minus 3 times something approaching 0. So overall, this is going to be a -3 over 1. So answer is -3. Part B. I'll write the problem. I already said above which form it is. So we apply L'Hopital's rule, taking the limit of the derivative of the top, derivative of the bottom. So let's see. Derivative of the top is 3e 3 to the x by the chain rule. That's a chain rule thing you might be able to do in your head. Because you say, if it was just e to the x, the derivative would be e to the x. So I'm going to have e raised to the inner function times the derivative of the inner function. Derivative of 3x is 3, so I just put it over here. Derivative of the bottom, chain rule, I get -4 over 1 minus 4x. You know, every time I get like a fraction inside a fraction, I always try to do something about that. So let's rewrite this as 3e to the 3x times 1 minus 4x over minus 4. That's better. It equals the same thing. It's just a nicer form. And we have to ask ourselves, is this an indeterminate form? Do we need L'Hopital's rule again? Well, what's happening to the top and bottom? The bottom is just -4. As x approaches 0, -4 is just -4. What's happening to the top? This is e to the 0, 1 minus 0. I think that it's fine to just not use L'Hopital's rule and say this is -3/4 e to the 0, 1 minus 0. I know e to the 0 is 1, so this is -3/4. And that's the answer. So those were just a couple of extra little practice problems I wanted us to do. And yeah, these 0 over 0 problems and infinity over infinity problems, those are kind of the main indeterminate forms that we're interested in. You should also know the other two that we talked about rearranging into this form. So one more thing. I want to remind you, remember to only use L'Hopital's rule for indeterminate forms of the type 0 over 0 or plus or minus infinity over infinity. I'm going to underline the word only. When we stated L'Hopital's rule earlier in this lesson, it started with the word if. It said, if the problem that you're dealing with is an indeterminate form, then you can use this formula. That's what L'Hopital's rule says. So you should only use it in those cases. What happens if we use L'Hopital's rule when we shouldn't? I'll show you an example. In the problems that we just did, in those two that are still on the screen, we had to know when to use L'Hopital's rule and when to not use L'Hopital's rule. Like, we used it, I put the LH, and then like to go from here to here, we just, got rid of the 1. But to get from here to the answer, I looked at it and I said, I asked myself, is this an indeterminate form? And I concluded that it's not an indeterminate form and that I could just kind of put 0 in and evaluate it. What if at this step, when I had this, what if I used L'Hopital's rule again? What if I said something over something, L'Hopital's rule, something over something, L'Hopital's rule, and I just like always applied it? Would that work? Well, I'll show you. Above, we said this, okay? That's the correct answer. And the reason it's correct is because technically this is a rational function and 0 is in the domain. When you have a rational function and x is approaching something that is in the domain, you can just plug it in. So we just plugged in 0. We got -3 over 1, which is -3. If we tried L'Hopital's rule, this is going to be wrong. And I usually don't like to write things on the page that are wrong, but I'm doing this as kind of a warning to show you what happens. You would have, I'm going to put equal sign, but I'm going to put a question mark. Like, is this really equal? Is this going to get us the right answer? You would have a ddx of the top. You would have a ddx of the bottom. Remember, what I'm doing here is wrong. We should not be using L'Hopital's rule here. But I guess I would get limit x goes to 0 of 0 up top, -3 on the bottom. And then you'd say, oh, well, 0 over -3 is 0. This is the wrong answer. So the point of all this is to warn you, only use L'Hopital's rule when it's an indeterminate form. If you just use L'Hopital's rule on everything, you might accidentally do something like this. Let's see. Yeah, and actually, what if I just gave you this as a problem? This was a step that came up towards the end of part A of that problem above. But what if I just gave you this? It would be kind of sneaky for me to do that, but I could do that. I could give you this, and say, evaluate this limit. And then, we've been doing so many L'Hopital's rule problems that you might be tempted to just apply L'Hopital's rule to everything. You would apply L'Hopital's rule and you'd get the wrong answer. So be on the lookout for that. If you get a problem that's something over something, you should determine, is this a L'Hopital's rule problem, or is this just something that's more straightforward? Numerator is -3, denominator is 1. Answer is -3. All right, so only apply L'Hopital's rule where you're supposed to. Okay, so that was L'Hopital's rule. As I said at the beginning, this is still considered an application of the derivative. It's something we use the derivative for. It helps us solve a type of problem that we couldn't solve before. We really couldn't have done these at the beginning of the semester. So what else can I say? This kind of wraps up our chapter on applications of the derivative, and we're going to move on to another topic for the next lesson. So we've got that to look forward to. L'Hopital's rule is just kind of a one-section lesson that it feels like it could kind of fit in at different parts of the course, but we had to wait until after we knew, after we were very comfortable with derivatives. So we put that topic in here. All right, so that's going to be it. As always, I hope that you're doing well, and I will see you soon. Take care.